Now we're going to see the demonstration of this example. So here's the folder with the image rotation source code. We have, as we saw before, two main source code files, main.c and mykernel.cl. We have another several folders under this directory. One has the images. This is the original image that we want to rotate. Also, it has a utilities folder that consists of several utility C code, which really help us to open the image in the BMP format and to do the all the other supporting functions. Also, we didn't talk about the AOCL_common. That is a folder specific to Altera OpenCL SDK. And this folder, it has source code related to the OpenCL specific functions for OpenCL platforms on top of Altera FPGA. So we're going to look at the source code briefly. And so we have the typical header file at the beginning for macOS and for Altera OpenCL platform. We have different header files included. Also, it includes the utilities functions provided as part of the image rotation. We also define the image path, where we can find the original image. The beginning of the main program, we see the similar things, the definitions of platforms, device IDs, context, command queue, program object, kernel object. We also have buffers for input image and output image. And we, in this example, assume that we are rotating this image counterclockwise 315 degrees. And these are the rotation parameters calculated. We're going to use mykernel.cl as my kernel source code. At the beginning of the main program, we open the BMP image file and we read in the images which was in BMP format. And this read BMP float essentially going to open that image file and do this format conversion. So we have a large array of floating point numbers stored in this H input image buffer. This is the buffer on the host. And we also get the rows and columns of this image, which we'll use for defining other buffers and also used in instantiating kernels. This is where we create the output buffer on the host, and we initialize this buffer by using some random number. At this part of the code, we have the same thing we did in the matrix multiplication example. This is where we query the platform. We find out the devices on the platform and try to use that device. And you can see that we do differently on macOS and on the Altera FPGA platform. After that, we'll create context that is bind to this device, and also for this device, we'll create a command queue. Following those, we will open the mykernel.cl kernel source code, and we will try to create the program using the source code for macOS. For Altera, we will try to open the binary, which was created by using Altera's AOC compiler. Next, we're going to build the program object and create the kernel object. We now specified a kernel function name, image rotate, which is the one we're going to use to perform image rotation. Next, we'll create buffers. We'll create a buffer for input image, and we'll create a buffer for output image. Now, note that both of these two buffers are device-side buffers because they were created using CL create buffer. And these are the buffers we use on the device side to store the original image and to store the output image, the rotated image, after the kernel is completed. We'll now copy the original image, which is stored in this image host side buffer. We'll copy all the pixel information to the buffer on the device side, which is named as input image. And then we need to set the proper kernel arguments. We'll supply the pointers to these buffers, output, input. We will also provide the dimensions of this image and also the rotation parameters. We will execute the kernel. As you can see that we're going to define the global workgroup size as the whole image. So we'll have this width and height of the image used defined here as the global size. For the local workgroup size, or the number of items within the workgroups, we can choose a number. Now we choose 8 instead of 16. Partly because that's the number we test out on FPGA side. And then we will instantiate the kernel using enqueue ND-range kernel. We'll provide the command queue, the kernel object, we'll choose the dimension, and there's no offset that we want to use. And then we'll supply the global workgroup size and local workgroup size. Again, here we're not using any events to synchronize with other kernel functions, so we'll just provide 0 now as the default arguments. Note that here we check the return value to make sure that this enqueue kernel ND-range kernel is successful, especially when you do this on the FPGA side. At this point, we assume the kernel is completed, so we can read the output data back to the host. So we'll use the pointer to the global memory on the device side, and also we'll provide the host buffer, and to also provide the size of the result. The next 3 lines are really used for storing the image into a BMP format. There's a little bit formatting conversion. There's a little bit BMP formatting involved, so we'll use this utility function write BMP float, which takes in the image in a linear array and the size of the image and then the name of the image file. So this will be this function will create the new BMP file that can show the result. After that, we'll do the best practice to free the host resources and also free the OpenCL resources. So that's the main function. Kernel function is the same that we described in the lecture. So it takes in the destination buffer pointer and source buffer pointer, the dimensions of this image, and the rotation parameters. And it will get the original coordinates of this pixel using 2 dimensions, so 0 and 1. Then we'll use the formula to calculate the new coordinates of this pixel. And after that, we will assign the pixel value to the new location. But before we do that, we need to do this boundary checking. And then eventually we will do the copying of the pixel information from the original location to the new location. So let's just build this program and then see how it works. So we'll build This again is on the macOS side. You might see different things when you build this on the Altera FPGA platform. And then we'll just run it. So we can see that we have read the original image, which has 720 by 1080 pixels, and the output image has been computed and it's saved as cat rotated.bmp. So let's check the results. This is the image rotation folder. In the this image folder, I have this original image, which you can see that this cat is the one we're going to do the rotation. And we come back here. This is the picture created after the rotation is done. So we can see that we essentially turn the image clockwise by 45 degrees.